Alright, welcome back again to this video lecture for our topic number 1. And this is our last problem for this topic. This problem is taken from the textbook by Creeth et al., Heat Transfer Principles and Applications. And this is actually problem 1.23 and 1.24. So I just combined the two problems because they're actually connected. They're chain problems or somehow similar. Okay, anyway, the problem says that a spherical vessel. Here's our spherical vessel. So now we're dealing with spherical geometries. 0.3 meters in diameter and is located in a large room whose walls are at 27 degrees C. So here's our spherical vessel and here's our walls. It's actually room. It's a room. So we can just close it or I don't know. But this is the temperature of the wall is given as 27 degrees C. The vessel is used to store liquid oxygen at negative 183 degrees C. Okay, so here the temperature at the vessel is negative 183 degrees C. It's storing liquid oxygen, and the temperature right here at the wall is 27 degrees C. Now, assuming that the surface of the storage vessel has an impedances of 0.1, okay, impedances of 0.1, determine the rate of the operation of the liquid oxygen in kilograms per second and pounds per hour, assuming that convection can be neglected, and the heat of vaporization of oxygen at negative 183 degrees C is 213.3 kilojoules per kilogram. Okay, so the scenario is that we have here a vessel that's containing a liquid oxygen, and then because of the heat transfer from the surroundings, actually from the wall, there's gonna be heat that will enter the vessel, the spherical vessel, and that heat will actually vaporize the liquid oxygen. So that's why this one is given. The heat of vaporization of oxygen is 213.3 kilojoules per kilogram. So this is a change of phase. So this is not Q is equal to mCp delta T, but rather another heat equation. Maybe, or I think this is gonna be. Let me explain this first. So the Q is equal to mCp delta T is this equation is for sensible heat, and this refers to any heat related to the change in temperature. So like this. So from, let's say, 27 degrees C to 90 degrees C. So that's the sensible heat. And another heat is in this region. That's the change of phase, right? Change of phase. And the heat that we call for this change of phase is the latent heat. Okay, so latent heat of vaporization in this, or if we are referring to this latent heat for freezing. Okay, so our problem says that because of the heat that's entering the system right here, there's going to be vaporization that will take place. So determine the rate of evaporation of the liquid oxygen in kilograms per second and pounds per hour, assuming that convection can be neglected. The heat of vaporization of oxygen is at at negative 183 degrees C is 230.3 kilojoules per kilogram. Okay, so this is a radiation problem because we have this value or we have this word emittance of 0.1, and we have surface temperatures between two surfaces, and it says that we neglect convection heat transfer, and as well, since a vessel has also a wall thickness, then we can also neglect the conduction right here. So how do we solve this? Then First is, let's convert all the temperatures from degree C to Kelvin, because if we are dealing with radiation, then we have to solve in terms of absolute temperatures. Alright, so here's our T sub 1, that's the temperature of the vessel, and here's our temperature sub 2, that's the temperature of this wall. So if we convert that, this negative 183 is equal to 90 Kelvin, and this one is 300 Kelvin. So therefore, the heat will be going from the wall to the vessel. And recall that the surface area for a sphere is 4 pi times r squared. Okay, so solve for Q absorbed. Okay. We'll be solving first for the Q absorbed using heat radiation equation for Q absorbed using heat radiation equation. Alright, so here's our equation is equal to the epsilon times this Boltzmann constant, Stefan Boltzmann constant, times the area times the difference in the temperature, but this is raised to the fourth, T sub 2 to the fourth minus T sub 1 to the fourth. Okay, so this is heat exchange, radiation exchange between the wall and the vessel. This is 0.1, and the sigma, the Boltzmann constant, is 5.67 times 10 to the negative 8, and the area is, this is 4 pi times r squared, and our r is half of 0.3 times 0.15 squared, right, times the temperature. Our temperature is 300 to the fourth minus 90 to the fourth. Okay, so I just didn't write the units, but you can also check the units if you want. Just take note, this is Kelvin, this one is in meters, and this one is in some appropriate units. So if you do the math, what we'll get is 0.1 times 5.67 times 10 to the negative 8 times 4 pi times 0.15 squared sorry for this, it times this, so times 300 to the fourth minus 90 to the fourth. What we get is 12.88 watts. Okay, now that we have the watts, then from the system, now solve for the mass flow rate, using thermodynamics. Okay, so it's something like this. So we have this vessel right here, and we have, let's say we have this liquid oxygen, and heat enters this at 12.88 watts. So because of that, there's gonna be evaporation of the liquid oxygen. So what's gonna be the mass flow rate of this evaporation? So therefore, we can just solve that using the latent heat Q. If this is heat rate, then this is the mass will also be mass flow rate times the latent heat of vaporization. HFG is just simply because the subscript right here, this is F and this is G in a steam table. So Fg, so that's the latent heat of vaporization. Now we have this and we have this H, so therefore we can solve for the m dot. So this is H of G, this is 12.88 watts divided by the given value of 213.3 kilojoules per kilogram. And of course, if this is kilojoules, then we need to divide this by 1000, or let's multiply this times 1 kilowatt all over 1000 watts, right? So this is it. And what we get is 6.04 times 10 to the negative 5 kilograms per second. Okay, so that's the mass flow rate. Now if we are going to solve using solve for the IP units, then we need to, let's try converting from here. Although we can actually do we can just convert this to pound per hour, but we can also do converting from here just to practice. Try to convert watts to BTU per hour. Okay, so this is 12.88 watts, and here's our conversion factor, 1 kilowatt. Alright, so let's convert this to kilowatts times the conversion factor of this kilowatts. Then this is 1 kilowatt per 3412.14 BTU per hour. Okay, so you can do that, and Q is therefore equal to this one in BTU per hour. 12.88 divided by 1000 times 3412.14. So we have 43.95 BTU per hour. Alright, and once you have that, then of course you'll be needing values from the IP units. Anyway, the summary of this is that, if we recap what we did in the solution, is again, because of this heat transfer by radiation, then it causes the liquid inside the vessel to evaporate, and we are asked to find the rate of evaporation, the mass flow rate. And so first what we did is to solve for this radiation heat transfer using the radiation equation, basic radiation equation. And after that, then we apply the thermodynamics principles to solve for the mass flow rate. Okay, so in the next for our next topic, we'll be discussing the combined modes of heat transfer. What if there's going to be conduction, convection, or radiation, or combined convection and radiation, something like that. Then we'll be solving problems as well regarding that. However, it's not yet the it's not yet the full details for conduction, convection, or radiation, but rather somehow that's the method that we'll be discussing in the next video, or in the next topic, will be beneficial in future computations. Even in other courses. Okay, so I think that's all, and thank you for watching these videos, and see you in the next video for our next topic.